Okay, kids. So this time I want to talk a little bit more about the mantle's layers. The mantle is below the crust, above the core, between the crust and the core. And how do we even know what's down there and what material it is and so forth? And so and why do we divide it into different layers? More importantly than anything, why do we divide the mantle into different layers? Why do we divide the crust into its own layer? Why are the cores their own layer? And the answer is chemistry. That's why we divide it into different layers. And how do we know where the layers begin and end? Seismic waves. I'm going to talk about two different types of seismic waves that we study the most, and then I'll talk about a couple of other types of seismic waves that we don't study very much anymore because we found out that they're just complicated versions of the other two. So, the Earth is divided into layers based on chemistry. Silicates are at the surface. The silicates, the basalt, the granite, the quartz, they're all silicon and oxygen. SiO2, SiO4, it's chemistry. The different layers are different chemistry. Below the silicates is the mantle. The mantle is iron, magnesium. Different chemistry, different materials, iron, magnesium. And there are some silicates down there, but most of the silicates float up to the top of the mantle and join the lithosphere, or the crust, and the asthenosphere below that. I'm not even going to edit that out. I won't even pretend that I'm going to edit that out. So the core, the outer core, iron and nickel, and the inner core, which is the liquid, and the inner core, iron and nickel, which is a solid. The inner core very much denser than the outer core. And so the different chemistry determines the different layers. And I'm going to ask on the test, how do we differentiate layers? Chemistry. But how do we know those layers exist? If we can't go, the farthest down we've gone is 12 kilometers. That's not even 12 miles. And that hole was dug by the Russians to do nuclear warhead testing so they could drop it down there without the nuke coming all the way back up and polluting the environment. Because the United States and England tested nukes in the South Pacific on islands that had no life on them. That radiation drifted. There was some serious problems caused by those nuclear bomb testing. So 12 kilometers down, you can test a nuke without it affecting the environment above very much. And down there's a lot of heat anyway, so it's not like it's going to make a difference to the planet. And so the deepest we've gone, 12 kilometers down. And, that's pretty far. By the time you get down there, the metal of the machinery that's digging just starts to melt, and there's just no way. You'd have to dig by hand from that point forward. You wouldn't survive it. So, how do we know what's below the crust? We can dig up in the crust and see what's in it, but how do we know what's below the crust? Every time there's an earthquake, thousands of seismographs, seismic wave sensors, around the Earth, thousands of them, detect that earthquake at different times. The closest seismograph detects it pretty much immediately, within a matter of minutes. The farthest one, the one across the planet, detects it minutes to hours later, usually hours. Sometimes it doesn't detect it at all. That's because the liquid core takes a wave traveling this way and bends it into a different direction. And so we know there's a liquid core because of a refraction of seismic waves. The bending of seismic waves off of their original path is called refraction. If you take the Pink Floyd Prism album cover, and the white light comes in and the rainbow comes out, because the white light was bent into different beams of different colored light. Well, a seismic wave doesn't split into multiple waves when you bend it, but it does change direction. So seismic waves traveling through the Earth, and the speed they travel at, and the amount they bend when they change layers, tells us the density of the material, which tells us the chemistry of the material. As long as we know temperature, we know the density and the temperature, we can tell you the material. And so we know what's under the Earth by the path of the seismic waves. So the two types of waves I'm going to make you learn that I want you to memorize. S waves are called secondary waves, and P waves. You're called primary waves. Primary waves arrive first after the earthquake. So you have a sensor way over here and an earthquake over here. The P wave gets to the sensor first, primary wave, P wave. The S wave gets to the sensor second, secondary wave, S wave. And I want you to know the difference between the two. I'll tell you those differences when we study earthquakes later in the year. But I want you to know, primary means it shows up first, and it's called a P wave. Secondary means it shows up second at the seismograph, and it's called a secondary, or S wave. In the mantle, the layers are a little more complicated than I said last week. Lithosphere has the crust, the asthenosphere, that's lithosphere. That's the crust and upper mantle. That's lithosphere, the solid parts. The mantle is the upper mantle, including the asthenosphere, part of the lithosphere. The upper mantle, the part of the mantle that has the most convection is called the transition layer, and the lower mantle. And then there's a layer below the lower mantle called the differential layer, or D layer. And the reason it's called that is some days it's liquid core, and some days it's solid mantle. So you have this layer at the top, upper mantle, asthenosphere, kind of plasticky, moves when the earth cracks open and magma comes out. That's the asthenosphere moving. You got right below that, that's the upper mantle. Right below that, the convection center, the transition layer of the mantle where convection is happening. I'll put convection up somewhere on the screen. We'll see if I finish that properly. And then the bottom layer of the mantle, D layer, might be liquid one day and solid the next. It might be part of the liquid core in the morning and a solid part of the mantle in the afternoon. It might change daily, it might change once a month. We never know. It's called the differential layer because it's always different than it was the last time we saw an earthquake wave move through it. We never know. Sometimes it melts, sometimes it solidifies and freezes, crystallizes and freezes. All right, so that's a little bit more detail about the mantle than I gave the last time. All right, something I need to add to the Earth's layers presentation. When an earthquake happens, let's just say California, because everybody knows they happen there. When an earthquake happens in California, you can sense it on a seismograph in India, in China, in Maine. Everywhere that has a seismograph will detect that earthquake. The farther the seismograph is from the earthquake, the longer it takes for the wave to get there. And remember, the P wave, the primary wave, arrives first, and then the secondary wave. And the distance to the sensor determines how much later the S wave arrives than the P wave. And so, if the wave from the earthquake goes through the earth into the liquid core, certain waves don't arrive on the other side. So it's called a shadow zone. If you look at, I'm going to post a picture of it. A P wave, a primary wave, will pass through, let me make sure I get this right. A primary wave will pass into the liquid core. If it's traveling like this, it goes into the liquid core, bends, and goes in a different direction through the liquid, and then bends back. So it goes solid, 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 liquid, solid. It changes direction, then it changes back to the same direction it was traveling in before, unless there's a lot of lensing going on, which means the shape of the object is round. Well, the Earth is round. So in the Earth, because of lensing, it's traveling through the Earth and it bends, and then it passes out and it passes into the liquid core, bends, changes direction, and then bends again and changes direction again into a totally new direction. That's because the Earth is round, not square. If the Earth were square, it would bend and bend back. But that's how lenses work. That's how prisms work. But the Earth is round, so it works a little differently. And so there are places where the P waves get bent away from certain seismographs. And when the S wave goes into the liquid core, it stops. It's done. It doesn't go anywhere. It is absorbed because there are different types of mechanical waves. So, important for the test. P waves can travel in liquid, S waves cannot. P waves can travel all the way through the Earth, S waves stop at the liquid core. So there are places on the Earth, if there's an earthquake in California, for example, you can get a shadow zone across the Earth from California where the S waves and P waves, they never go there because the P waves have been bent away and the S waves have been stopped. So the shadow zone, definition on the test, shadow zone. Location on the other side of the Earth from the epicenter where the P waves and S waves don't ever register on a seismograph. Shadow zone. Place on the Earth where an earthquake's waves never reach that spot. It is because the liquid core deflects the P waves and absorbs the S waves. So hopefully that makes sense. I can't believe I left that part out. It was like the third slide. Anyway, I'm going to get to the magnetic fields one later.